So in the wildlife, reaction diffusion kind of shows how patterns develop, and it's the interaction between two chemical substances in their skin scales, which causes the different and wide range of patterns that's shown in wildlife and nature. And so that's what our project will be modeling.
So in class, we observed pattern formation using the Gray-Scott model and the FHN model. So as a quick recap, the Gray-Scott model consists of two partial differential equations with diffusion and a nonlinear autocatalytic reaction that consumes U and produces more V. The equation for U also has a term that replenishes U from an external reservoir, and the equation for V has a term that removes it from the system. From these equations, we saw that we can produce a wide variety of patterns. We also used the FHN model as another reaction diffusion system in class, and we applied it to observe how these patterns behave on irregular domains. This connects to Turing pattern formation, where a uniform steady state becomes unstable in the presence of diffusion. This normally happens when diffusion rates are sufficiently different, so generally when the diffusion rate of V is much, much larger than that of U, which leads to more complex patterns. For our project, we analyzed the article, "The Leopard Never Changes Its Spots," which takes a different approach. They focus on simplifying an older, more complicated model to make it an easier model that is sufficient for just simulating the formulation of patterns. So they start with Turing's nonlinear reaction diffusion model and reparameterized it to reduce the number of parameters and better control the generated patterns. They replaced dA and dB by R, which is equal to dA over dB, and they added S, which is just equal to the diffusion rate of B. They also fixed SP to be equal to 1 since they found it to be confusing, and it affected the perceived scale of the pattern and the velocity of the simulation at the same time. So then instead to adjust the pattern scale, they just use S. And then to simulate the patterns in the model, we have to impose bounds on the variables to keep the system stable. Their approach is to use an approximation of tissue growth using discrete matrix expansion operations, and this leads to the biggest difference between the two models that we use, which is the Gray-Scott and the FHN model models chemical reactions and diffusion on a fixed domain, while the article's model models pattern formation and domain growth together since they have that discrete matrix expansion built into their system.
So for our code with the sliders, we had variables that we used that we could change, and we had S, which is kind of our scale or our dB, and then R, which is our ratio, which is like dA over dB, and then we have our delta T, so you can see time and how it changes. And so essentially a higher S kind of scales it, so it makes it smaller, like smaller groups in the pattern, and then a low S makes bigger groups in the pattern, and then a high R kind of does faster diffusion, so it makes it more mixed, and then slower diffusion for a low R, which makes it less mixed, and that's as you change delta over on. Because at a low delta T, so our time hasn't changed much, you can see that it's random, so even if you put in the same parameters and delta T is 0, it's going to be something different every time because we have a bit of noise to our code, and that kind of shows how in real life and with animals there's some genetic variation and randomness within how they develop, and then as the chemical reactions happen, it leads to a pattern that's very similar to each other. That's why, you can see that two frogs are slightly different, but you can still say, hey, that's a poison dart frog, is because their patterns over time look the same, even though they look different beginning. And I think that's really interesting. So the first animal we will be going over is the yellow-banded poison dart frog. And as you can see, the yellow-banded poison dart frog from our article model, it's a bunch of stripes, and then slowly those stripes start to get spots in them. Our model that we used in class is the Gray-Scott model, and it shows the spotted nature of the poison dart frog. And then our model replication shows that how phase 1 ends at step 4000, which is mostly the creation of those striped lines, and the matrix expands over time during phase 2, which is our tissue expansion, and then the stripes turned into dots more over time as the tissue expands. The next animal we will be going over is the reticulate whipray, and the reticulate whipray, as you can see in this article, kind of has a bunch of dots that slowly turns into kind of like a maze-like structure with a bunch of lines. Our Gray-Scott model shows the end result with all the maze-like structures in it with not very many dots. And then here's our model replication. The colors are flipped for it, but it does show how there's a bunch of dark dots, and then it slowly turns into like a dark maze-like structure. The next animal we will be going over is the 13-lined ground squirrel. And as you can see, the 13-lined ground squirrel is very similar to the poison dart frog, as it has these lines that go straight across, and then it starts getting the dotted nature in it. And the Gray-Scott model we did over in class, it showed the dots, but it also showed how there was a different generation pattern forming of the lines, and it was kind of like 2 generation patterns together. So for our model, it isn't exact because that's due to the extreme mixing between the spots and the stripes that you can see our model is trying to recreate, because you can see how there are some dotted parts and some striped parts in our model. And then further steps with these results is they can help with AI training and helping to try and generate animal patterns on, animals that are accurate to how they're created. And these patterns can also be used to generate the patterns in case of animal extinction when we can actually reference the animal itself. And it'll help us further learn about genetics and pattern creation of other animals.
Let's dive into the code behind the simulation results. The parameters for each simulation are taken from the article data provided. Each simulation had different starting parameters. The chemical reagents A and B are created using uniform random distributions. The simulation loop goes through thousands of iterations and calculates the Laplace diffusion for each chemical. For the tree frog and squirrel, we check to see which phase of the simulation we are in and use the correct Laplace diffusion for the calculation. This is because of the boundaries are different for the 2 Laplace calculations performed. This calculation is used in the equations we saw earlier for the specific model mentioned in the article. Then the matrices containing each chemical are updated with their new values, and any extreme values outside the data range are cut out. For the tree frog and squirrel model, we used matrix expansion to force the stripes to develop in phase 1, and then expanded with the growth during phase 2. During our simulation, we checked to see if the model has made it past the specified number of iterations for the first phase, and if so, then we expand the matrix during each growth step. Finally, after the simulation is run, we take all of the graphs we have saved at specified steps given in the parameters and plot them for the user to view. While plotting, we took the median of the data to use as a threshold. This threshold allows us to represent the graphs with 2 colors for the users to easily see the resulting patterns.
So since our project mostly focused on approaching pattern formation from a different angle, the physics concepts we covered were largely the same. So we observed reaction diffusion systems and then the Turing patterns or instability, which caused more complex pattern formation, and then also the emergence of complex structures from simple partial differential equations.